Hello. Yes. But it's a second prime. No. It's not. No, I found it very interesting. Like sometimes the dictations that honestly may not be different. Yeah, no, that's prime for yeah, but also for transport. Yeah, that's can be. Yeah, I use it for say a change in various situations. Like yeah, so we use prime. But yeah, in that the don't use prime. Yeah, but it can vary from like I heard with prime to now. Yeah. And this one is real different. Like it was one. Yeah. So initially yes, but then I. There must be some difference. What started not like insurance come. Oh, for point? Yeah. Yes, because so what does that mean? You have one. Yeah. That's right. It's just. And also, okay, so one difference is like intervals. So in English, you have like 1, 2, and 1 if the limits are not included. Right. But in France, you would have, I think it's like this. Oh, I've seen that one as well. Like yeah. But so then, obviously, again, you don't need other stuff there. So it's yeah, it's I'm starting to like more. The thing is, everything is just so overloaded. As long as you're consistent, it makes sense. Yeah, that's the whole idea. Okay. So I was planning to talk about a partial derivative with more variables, but yes, seeing how it was not easy last time, just doing some optimization, I thought, okay, let's take a break and have another topic that's not easy, but different, and then we can come back to it. So yeah, that's just the two last things that I want to see. So Taylor series and just then partial derivative of more than one variable. And then we're good to go for the exam. So it's just going to be, yeah, and exercises for now. Okay, so Taylor series, what's up with that? Well, Taylor series are approximation of difficult functions. Can be of many variables, but we start with one. It's easy to generalize with polynomials. And why do we do that? Because polynomials are so easy and other functions are not so easy, both for humans and for computers. So just call messy nonlinear function like exponent log sine. So I haven't talked about sine and cosine because we don't use that all that much in economics, but or even rational functions, so something like 1 over x, many different things. If you can approximate them with polynomials, that's much, much easier. So like this, so we're going to have f of x would be equal to, so instead of having cosine, you're going to have an approximation of cosine or an approximation of x exponential, which would look like any polynomial. So C0, some constant, plus C1 times x, plus C2 times x squared, plus C2 times x cubed. So you see what I'm saying there? So the nice thing with that, of course, is you just have whole numbers as exponents. And then when you take derivatives, then everything simplifies very well. We know the rule. It's easy to deal with. Yeah, so why we do that? It's polynomials. Easy to compute for humans and computers. So this, you might be thinking I'm kidding, but I'm not kidding at all. And to take derivatives. Yeah, so think about back in the days when we didn't have a calculator. So now it's trivial, you bring it to the exam, but back in the days they didn't have one. So imagine computing something like log of 4.5. Good luck. Really, that was something that people struggled a lot with it. So if they could find tricks to compute it very easily for any function, that's very good. And nowadays, we always use that for many instances. So some of you know the game Quake 3 Arena. Quake 3 Arena? No? It's a game, well, basically you have a gun in front of you and you shoot monsters and you shoot people. And so anyway, so that's a computer game that was very famous early 2000s. Yeah, it broke ground. But what was especially good about this game, it was extremely fast because you didn't have. So the old days, you had one other game that was called, I think, Duke Nukem. No, you're not a fan of computer games. Anyway, so Nukem was nice, but it was super slow. So you have 1 frame per second or something. So it just takes forever. But Quick 3 was instant. And people were amazed because you have all these colors and all these textures and all these lighting to show. So the whole 3D scene. And it was so extremely fast. And one thing that's super difficult or takes time to compute when every time you show some scene with lights is you need we've been talking about the gradient. So you need the gradient of the light source when it bounces on the surface. And many times, like for every pixel of the game, you had to compute something like 1/√x. So you had to compute this all the time. If you just have some lousy algorithm to compute it, it's just so slow. But then they had some genius programmer. Nobody knew who that was. It's still a legend. Nobody can. But at some point, they put the code of Quick 3 Arena online, and people were checking it. And at some point, they found the algorithm to compute this, and it was blazingly fast. It's really a genius. So he made some operations with how numbers are expressed as floats or as in the computer. Plus, he used Taylor series to. So he starts with some approximation, and then he used some Taylor series to make it better. And it's yeah, not Taylor series. It was some Newton method, but it's related to that. And yeah, and it made it very quickly, very quick. So you may think that your computer computes all the functions in the world. It always takes approximations. Otherwise, you would be just waiting forever. Okay, so that's what we're going to see today. So so math is all about generalization from examples. So let's start with an example. So let's approximate. So let's have log 2. So log 2. Somebody knows? I don't know it by heart, but I have written it there. So, and I have a computer. So what is log 2? So log 2 is, it's less than 1. Yeah. I have to write 2.0, so it's going to give me. Okay, so that's this. So let's just say it's approximately 0. Okay, so we want to get to that number, but we don't know how to compute logs. We forgot, we don't have a technique to do it. So let's think about the good way to approximate it. Well, first of all, I'm going to cheat and we're going to look at it. So just to know from where we start. So this is log 2. So this is the logarithm. Okay, so what's a good approximation of log 2 that we would know about? What? Yeah, so just look at this, and is there some point that on this curve that's not as hard as the other to find? Yes, 1. So 1, why would we use 1? Well, first of all, we know exactly what log 1 is. It's 0. So this, you know it by heart from childhood. And second reason is it's not too far from 2. So if we knew a lot about log 100, okay, but 100 is quite far from 2. So 1, at least we get 0, which is in the ballpark. So obviously that maybe, I don't know what approximation you like, but essentially what we're trying is to start by from some number which we know well, and then approximate some value that is not too far. So good first approximation. Log 1, which is equal to 0. So why? So 1 x equals 1 is close enough. And we know a lot more x at x equals 1. And so what Taylor, well, before him, Maclaurin and other people, so many people that worked on this problem of approximating functions. And so what he did is he said, okay, let's look at the function and find the best way to find approximation for something that's close by. So Maclaurin said, oh, we're going to start at 0, but then what Taylor said is, he said basically, oh, we don't have to start at 0. We can start with any number we know. So here we know 1, so let's start at 1, so it's easy to approximate 2. Yeah, exactly. So they were more or less at the same time. Okay, yeah, you find 0. So 0 is unfortunately smaller. It's too small compared to our real value. So problem. Ln is smaller than ln 2. Those I already forgot. 0.693. So why is that the case? Why is it the case that here we get something that's too high compared to our starting point? What? Yes, exactly. So we started with this number there, but so if the function was perfectly flat, not changing at all, then log of 1 would be equal to log of 2, we would be done. But unfortunately, it looks like it's increasing over not over time, but as x increases. And so when we get to 2, then the function is no longer 0, it's higher than 0. So what we essentially see is that the slope of the function at 1 is positive. So when we travel from 1 to 2, travel 1 unit to the right, then we travel some distance upward. So what solution could we use to improve our guess? Somebody has an idea, they can say it, otherwise I'm going to say it. How should we exploit this? No clue. Well, if I know, by the way, Mohammed is the only person at home, so Mohammed can help us too. But if I know the slope here, well, I can see, well, maybe the slope is some number that I know, and then I can more or less approximate the change from 1 to 2 with the slope at 1. And then I'm going to get a number that's a better approximation than just assuming that the slope is 0. I know it's not 0. So any slope that I can compute should give me something that's a bit better. So solution using we know slope at equals 1 is positive, and we know the distance between two and 1. Which is 1. And so what I'm going to say is rather the following. So log2 is approximately equal to log1 plus, well, the rate of change at 1 and over this distance right there. So what's the rate of change? It's d log of x dx, but at 1. And then how much do I move? I move from 1 to 2. So the distance is 2 minus 1. Okay. So yeah, maybe I have to unpack a bit more here. So this is how much my function is changing for every unit, but exactly at 1. So it's not perfect, but it's better than nothing. It's before I was assuming that this was 0. So because I was only taking this. So this is okay, but I can do better because I know that this is non-zero. This is some positive number. And plus, I know how to compute it well. So what is, if I have f of x equals ln of x, what is this derivative there? What is f prime of x? Yes. So it's 1 over x. So f prime of 1 is 1 over 1. So it's equal to. So then this there is times 1 times. So this is equal to 0 plus 1, 1. So my second guess is 1 instead of 0. So is 1 better than 0? Well, I have a picture there. What I just did. Yeah. So if I take the first order, the 0th order approximation is just log of 1, I get 0. But then if I know the slope here and I know that I move 1 unit to the right, then I get a value of 1 instead of 0. So is 1 better than 0? Yeah, it's closer to log 2. But of course, we could do better than that. So 1. But not perfect. Okay, so question so far? You see the goal. The goal is always starting with something I know and trying to sort of shoot in the direction of the number I care about, which is 2, by taking as much information as I can about the shape of this log function. So here, we're going to say the first order approximation is just, yeah, it's just essentially this line. So you see that if I took an approximation at 10, then that line would be way, way, way too high. It would be equal to 9. Yeah, and log 10 is nowhere close to that. But since I'm not too far, then you see that I get something. If I was interested at 1.5, that would be even better than that. Right? And so why is this? So first of all, is this is 1 bigger or smaller than log 2? Yes, it's bigger. So why did I not? Why did I get something that was larger? So why is one not a perfect approximation? Why is the first order approximation, which is equal to one? Yeah. So yes, exactly. So what you're saying there is that the slope may be one here, but then it's change. It's becoming smaller and smaller and smaller as I approximate. I approach to. Exactly. So that's exactly the reason is. So a first order approximation is better than a zeroth order, but it would be perfect if log 2 was just some linear function, then the approximation would be perfect. Unfortunately, here it looks like we say it's concave. It's concave relative to the x-axis, or in other words, the second derivative is negative. So the slope is actually very high, very high, very high. Then it's one, and then it's decreasing, 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 decreasing. So then, what should I do? Well, I should take care of this. So I should take higher orders of the function. All right. So Taylor's idea. So reason. So second derivative is negative. So we should include okay, so this is where we're going. Now I'm just going to tell you what Taylor's idea is actually. Yeah, so just the general idea is the following. So Taylor's idea. So approximate a function f of x, which is here log x, around some value, x0. Here it's around the value 1, with a polynomial expression of this form. So here x which looks like this. Equals to some constant 0 plus some constant 1 times x minus x0. And then you include higher order terms. So plus some constant 2 times x minus x0 squared. And then you can go on and on and on and on with as many terms as you like. Yeah, and since here I'm adding things that are completely nonlinear, then it's going to capture better and better and better everything that's nonlinear about my function. So I'm going to define this g of x to be the best approximation I can. Let's add just one more. And then, so there's only one thing to identify in G. It's these constant there. So this I know it's my starting point I've just chosen. This is the value I care about. So in our case, this is 1, x is 2, and f of x is the x. And then the goal is to find what are these optimal constant terms. question there. X0 is our starting point. So here X0 is 1. So it's something. So I care about X is 2 is something I want to know, and X0 is the starting point of my approximation, which is hopefully not too far from what I care about, and at which point I know stuff about my function. Again, if it's Maclaurin, that's just a special case where the starting point X0 is always 0. But so there's just no hope of using this to starting at 0 to find log 2. There's because it's not even defined. So we have to start somewhere better. Okay, so and what is the best? So the best approximation. Well, there are many different sorts of approximation, but with this form, the best approximation of x by g of x is such that is as many derivative as possible match. At x equals x0. So just again to reiterate, here we have the first C0 would be just log 1, so it would be 0. And then the first derivative would be the derivative of log x. But then the second derivative would be the second derivative of log x at 1. And then the third derivative, the fourth derivative. And what Taylor shows is that you can approximate absolutely any function you like as long as the derivatives exist and in the neighborhood of 1 at this value exactly. So, so you can have a fourth order, fifth order, and you can match things very, very well. So let's just find the mysteries C0, C1, C2, C3. So what do we mean by this? We mean that G of x0 equals f of x0. And then the first derivative of G has to be equal to the first derivative of f, always at x0, and then the second. Let's just go to 4. Okay, so if we have that, then G is going to be very, very good for approximating f close to it, because its change and its rate of change and its second derivative are all going to be the same at x0. So if you're close to x0, it should be pretty good. So let's go ahead. Let's find the derivative of G. So G of x is this. Then the first derivative is equal to so if I take a derivative of a constant term, it disappears. Then I take the derivative with respect to x here. So then this x0 is nothing, but this, so here I get only C1. I can just show you just to be clear. C1 x minus 1. So this is a constant, this is a constant. And then the derivative with respect to x just gives me C1. And then, so the derivative with respect to x for this term, well, here I have a quadratic, so I get 2 times this to the 1. Yeah, and that's it. And then the derivative inside it is just 1, so that's 1. And then the derivative of that one is 3 to the 2, and then the derivative of that one is 4. Right? Haven't lost anybody? Yeah, everybody or some people. Okay, so it's just remind yourself of the rules of the derivative. The goal here is to just have a polynomial, because if, as you can see, a polynomial taking derivative is you just take this in your sleep. It's very easy. Okay, and then the second derivative. C1 disappears. Then I have only this x here, this x0 doesn't matter, so this disappears. Then here I have a quadratic, yes. So I have 2, and then I have 4 to the 2. So yeah, I can just multiply them. So this is 6, this is, and then continuing. Third derivative. As you can see, more and more, the simpler it gets. So 2C2 disappears, then this is just 63. Then the quadratic there, so we get 24. Then let's take the fourth derivative. This disappears. And then this is just 1. So these are all my four derivatives. Obviously, I can take as many as I like, but you see the pattern. And then now I want to express them at specifically x0, because that's where I know where these values are going to be. So that's x0. So I just substitute x0 there. Yeah, sorry if you had hope of copying everything. I'm going fast today. So the goal is really to understand the reasoning. And here, what do we get? Well, we get that all of these are going to cancel out. All of these are going to cancel out. All of these are going to cancel out. So why is this the case? Well, it's the case because I'm exactly at x0, and at x0, so the impact of the higher order terms on the value of the derivative have not kicked in yet, because I start at 1. So if I was at 1.5 or at 2, then say the slope of the slope would be changing, but at 1, then it's not changing. So that's a bit of n waving, but just to give you the intuition of as to why all these terms are disappearing. At 1, I'm just going to have 1 terms for each. Or here at x0. So here, all of this is going to disappear. And then all of this is going to disappear. So that's quite simple. And then I'm Yeah, so then what are my coefficients? The coefficients. So I wanted this thing. So GFC0 is C0, GFX0 is C0, C1. Then 24 C4. So let's just express the C. So so that's it. I found my my coefficients. Back in our expression. So, GRX equals so C0 is this. And obviously I could go for all right. So there's a way to express this more simply. So somebody sees it?
Yeah.
Yes, exactly. GRX is equal to F to the, I take the, oh, so it says infinite sum. No. F of I of X. So why am I writing this? Well, the zero derivative of F of X is just F of X. The first derivative is F1, the second derivative is F2, and etc., etc., etc. Oh, yes, so that's at X0 times, and then here I have X minus X0 to the 1, and then here I have X minus X0 to the 0. So I could just write it this way. And then here, as what was rightly pointed out, this is I factorial. So I factorial, so 1 factorial is 1, factorial is 1, 3 factorial is 2. What am I saying there? No, 0 factorial, sorry. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 is factorial is 6. So you see that it's every time all I have to do is the product of 1, 2, 3, 4, 5 until I. So that's the factorial. So n factorial goes to n times this one. So this is the all right. So this is an expression that somebody has seen this expression before. Yeah. So yeah. So that it's nothing mysterious once you see how it comes about. So it's just we want to take derivative of some approximation, and we want to match as many derivative as we like around the point that we care about. So around the starting point to get something as close as possible to what we care about. And yeah, exactly. So that's this special case. Okay, so let's find now what we came to do. So back to finding log 2. So we have the first thing we have to do is compute the derivatives of log. So yeah, so I'm just going to write derivatives of f of x equals log of x. So f of x equals log of x. Then the first derivative is, as we have just seen, 1 over x. Yeah. Yeah. you're seeing already what's going to happen. No. It's going to be alternating in the f of I here. This is going to that for log. It's going the sign is going to change. Yeah. Yeah. So the second derivative. Somebody can tell me what this is? Yes. So just to remind everybody, so this is 1 of x. 1 over x is like x to the minus 1. So then the derivative of this is going to give me minus 1 x to the minus 2. So again, it's always so here it's always the same rule. So that rule is at least know that one, please. Okay, and the third derivative. Yeah, so here I have plus 2 times 1 over x cubed. And then, so I can just write. Then fourth derivative. Negative 6 over x to the 4th. Okay, so these are my derivative for any x. But of course, I start at some x, which is, but you see now that, yeah, if I didn't have to start with this, I could start with some x that is not so close or not so far, because these, well, they're still a bit complicated to compute, but not as bad as log. But since we have logs here, let's start at x, x0 equals 1. So we have 1. So that's 0, that's 1. So these two are already new. Then it's minus 1, it's plus 2, it's minus. That one is not too messy, so that's why it's nice to working with it. All right. So I'm just going to write it this way then. So log of 2. And then I'm really going to go for it and write equal, because we're going to allow ourselves to take an infinite number of terms. We won't write them all explicitly, but okay, so yeah, maybe that's not the best idea. Let's start with this form there. Okay, so this is 0 plus 1. This is yeah, negative. And this was 2. And this is negative 6. And then here I care this is 2. X is equal to 2. And x0 is equal to 1. So then I get this right here. So this is plus 2 minus 1, 1. Minus, so all of these are 1. 2 minus 1 is 1. So that's very neat. So I can just get rid of that. 1 to the 1 cube is 1. And then 1 to the 4th is still 1. Yeah, let's simplify a bit. So I get 2 over 6 is 1/3. 6 over 24, 1/4. Yeah, so you can see that this is the pattern. Yeah, if I add an infinite number of terms, then I'm going to have a perfect approximation. So let's just see what we get if we have all these terms. Yeah, 19 over 20. Oh yeah, you're right. I got the minus there. Yeah, 0. And what was our, so not too bad, not too far. Are you sure? Oh yeah. Oh, so that's quite bad. Well, it's not as, yeah, still better than where we started. So we need a big number of terms. And obviously, if you have one function that's very good is say sines or cosines around 1 or around 0, the approximations are quite good. Yeah, but that one is never going to be perfect because you always overshoot, undershoot, overshoot, undershoot. That's why we get these alternative signs there. All right, so log 2 equals 1. I have shown what's the picture there. Yeah, so this is with 4 second, third, and fourth order approximation. So this is, you see that at 2, if I have fourth order approximation, so that's the red line, you see I'm quite doing fine. If I had a fifth order, it would be even closer, but then at some point I have too many lines. All right, so here's some notes. So something to add, but it's really the main is there questions about what we've done so far? Now we've sort of nailed everything. For the exam, please learn this. So please learn this formula. It's a long one, but at some point, if you get the simple version, it's how it works. So f of x0 plus f prime of x0 times x minus x0 plus f prime over 2, and then third derivative over 6, etc., etc. And every time you take x minus x0. So yeah, I could have just showed you the formula, but I think it's nice to see where it comes from. And yeah, so Taylor is used in many places. It's used to prove many theorems in statistics as well. Most of the theorems in statistics at some point involve Taylor. So some note. So instead of expressing the polynomial with an infinite sum, we may simply add a remainder. So for example, second order Taylor approximation. So you would write something like f of x equals f of x0. More precise would be f of x0 plus f prime x0 and then just a second order terms. For many things that we do in math, it just first order approximation or second order is gets you quite far. So and then what you can see is I have something left is whatever I haven't expressed there. So you would write this R2. R2 is the remainder. Which error, the error of the approximation. So this is, there's no new notion in that. It's just a convention. You write it this way. If you want to use another way of writing it would be the following. So you could write just f of x is approximately equal to this, and then you don't have to write so it's just if you want to use an equality sign, you add this remainder. Yeah, so more terms. If you are smaller also note, as we've been saying, around x0 equals 0. So the Taylor series, the Taylor expansion is called Maclaurin series. in honor of Maclaurin, which was Colin Maclaurin, which was a Scottish mathematician. Oh yeah, by the way, I think we were talking about Jacobi, and I said he's German. Yeah, so you said Polish, I think? Yeah, so I was curious, and I thought, oh, maybe yeah, but I checked, and yeah, he's German. So. Turns out, Poland, they don't have a lot of mathematicians. Like, yeah. Yeah. So, yeah. So around the Hungary, they have a lot, but yeah, Poland not that much for some reason. Anyway, and also last point is a Taylor series. Maybe generalize more variables. But for this, we need tons of higher order partial derivatives. So yeah, partial of f with respect to x, with respect to y, with respect to x and y, x and y and x, y and y, and many terms. But again, this is very useful in many instances where we approximate stuff with higher orders. Yeah. Perhaps the most useful application is mathematical means. So now you can laugh at nerdy jokes. So Taylor is not that Taylor, it's that Taylor. All right. Okay, well, I'm a bit, last time I think I took like 2 lessons to talk about this. So, well, let's have some examples. So what examples would we take? What did I take something? Oh yeah, let me think what I took in the exam last time. Don't worry, I haven't started your final. Yeah, so it's going to look like this. We're going to correct this next time. Okay, yeah. So exercise for you. Prove that E is equal to this thing. I have no clue. I just tried it with E and I obtained that. So yes, it's. I think I was a bit. I don't know. I think I was mean to the students last time because just showing this in the exam and do your best. So that I think so. They got very good grades at the midterm, so I was kind of puzzled, and I thought, okay, let's hit them with some heavy stuff. But okay, so but try it. Try it for yourself. So I didn't even give you a starting point there. So what you have to do is imagine which starting point would be a good starting point to. So I'm going to say a hint using Taylor. Taylor extension. Yeah, that's E, right? Yeah. So, but that's yeah, that's like the definition of E essentially. Yeah. Yeah. Okay, I'm not too sure. So when I showed all the derivatives, at some point there was the derivative of E, and yeah, I was stuck, and I thought, okay, if I'm stuck, then let's not inflict this on the class. Yeah, but so I thought there might be something going on with this. The fact that the definition of E is that it's on the derivative essentially. But yeah, I may look at it. Okay, so please try that. You still have 10 minutes. Or some are trying. If I did ask this last year for the students, it means it's feasible. So I'm just going to give you some hints. The main thing to do is to find a very good starting point. Start with something you know about your function, and then you're good. This helps tremendously. I'm going to give you like 5 minutes maybe to think about it, and then we can solve it together. Oh, yeah, it's good that I'm showing the Taylor series there. That's because you haven't had time to learn it by heart. McLaren. Yes, you use McLaren. No, not McLaren, McLaren, but I think that's the right way to go. Somebody got it? Yeah, so the thing is, it's so easy to do, right? Just 2 minutes, and then I can show you what you have to do. Steve Stone, are you still with us? Are you making progress? It's not Steve Stone, sorry, Steve Sun. I don't know how you pronounce it. Okay, good. Oh, Timothy is there too. Oh, more people are there. I didn't know that. Oh, 5. Okay, I put 5. Yeah, I was quite mean last year. I'm going to be nicer this year. All right, so it looks like more people than that have finished. So what's the trick there? Where are we going with this? Or somebody from the audience that hasn't spoken yet? You, are you still with us? How would you demonstrate this thing? Yes, that's a bit. I think it's a bit difficult to ask this since we just showed the Taylor series. So yeah. Yeah. So let's go ahead and then show it. So what we are saying essentially is what we want to prove is that so it's we want to express f of x equals e to the x at equals 1. All right, so e is some function that is an exponential function. That's another not nice function to deal with, exponentials. And if you want to compute it at x equals 1, then it's get the 1 equals, so that's the goal. So let's express this. Oh yeah, sure. Yes. So let's have n or I. No, let's have I since we've been using I before. Sorry about that. You have good eyes. Okay, so let's start with let's do 2, and I think we're going to maybe 3 if you want. All right. So and now the only challenge, the only thing that's left is so we know what the function is e. We know what the target value is. It's x equals 1. The only thing that remains is finding a good starting point, x0. So do you know what Do you know some x such that E of x gives us something that we know about? What? No? Yeah? Yes. So the question was, so we want a good starting point. So a starting point at which we know a lot of things about our functions. So E of 1, E of 2, E of 3, we don't really know, but E of 0, we know. So good starting point. X0, 0. Because we get E of 0. So then we are we will have McLaren. Since we started at AC, but yeah, so shouldn't bother about that name. It's just a special case. So Taylor is the man. Oh, we're almost done. So let's go ahead and do that quickly. So E of x is approximately equal to E of x 0. What is the derivative of E of x? It's E of x. So E of x 0. And what's the second derivative? It's also E of x 0. And then my starting point, yes, is 1. So sorry, 0. Yeah, so I can write it this way. So I get that E of 1 is equal to, oh yeah, so sorry, this is 0. So E of 0 is 1. E of 0 is 1, so there's 1 again. And there's 1 again, so that's F. And then here I want 1, 1, and I could have another term there. So I would have 1 over 2 times 3, 1 over 6, etc., etc., etc. So I would get that, this result. Right, so I went a bit quickly because we were over time, but this is the spirit. Yeah, I was very, I don't know what my student did to me last time, but asking this for a final exam, it's not that nice. It's a very nice result because everything cancels out, of course. But yeah. All right, so I see you next week. So next week there's a single topic I want to cover, and then we're just going to do exercises. I don't know why I'm going super quickly because I never have questions, and yeah. How many? Oh, possibly, yes. Let me verify that. Yeah, well, exercises and reviews, and I'll see exactly what. So probably I'm going to go over the final and over all the quizzes I've given you. Yeah, sort of thing. Okay, I'll check that. If I have less time, I want to make sure that I do enough exercises. All right, thank you.